Module 8. Designing an ISPU-based roll pitch demo. In this module, we'll make use of the Intelligent Sensor Processing Unit, or ISPU, embedded inside the ALSM6D-SO16IS. We'll use the STM32 Cube IDE to implement the algorithm, which will run on the ISPU. The ISPU will read accelerometer sensor data and calculate the roll and pitch angles. We'll then use Algobuilder to display the calculated roll and pitch angles on the PC screen. The ALSM6D-SO16IS is a system in package featuring a high-performance 3-axis digital accelerometer and 3-axis digital gyroscope. It also embeds an ISPU, or Intelligent Sensor Processing Unit. The ISPU is an ultra-low power, high-performance programmable core with high computational efficiency. It can execute signal processing and AI algorithms on data from the sensors. The ISPU is compatible with most common development tools and can be used to implement both machine learning and deep learning on the device. It is equipped with 32 kilobytes of program RAM and 8 kilobytes of data RAM. It also features a floating point unit supporting addition, subtraction, and multiplication. Let's start by implementing the roll and pitch angle calculations on the ISPU using the STM32 Cube IDE. We will create an ISPU project using an ISPU project template. Open Windows File Explorer and navigate to C:\MEMS Studio Workshop \Module 8 \ISPU project template. Select and copy the ISPU folder. Then navigate to C:\MEMS Studio Workshop \Module 8 and paste the ISPU folder there. Let's now open the project in STM32 Cube IDE. Launch STM32 Cube IDE. You may be asked to select a workspace directory. The default directory shown should be OK, or you can specify your own. Then click the Launch button. If this is the first time you open Cube IDE, you may be presented with an Information Center window. This window provides easy access to news and resources for ST products. You can close this window by clicking on the X on the tab. Should you want to view this window in the future, it can be opened again via Help Information Center. To open the STM32 Cube project, click on File and then Open Projects from File System. Click on Directory to the right of Import Source and navigate to C:\MEMS Studio Workshop \Module 8 \ISPU Eclipse. Then click Select Folder. Make sure the Eclipse folder is selected and click Finish. This will open the ISPU template project. You should see it listed in the Project Explorer window on the left. Let's start by renaming the project. In the Project Explorer window, right-click on ISPU and select Rename. Call the project ISPU-roll-pitch. Then press OK. Let's now expand the project to see the project structure. In the root folder, we see 3 text files: conf.txt, meta.txt, and shub.txt. Conf.txt contains configuration information for sensors and the ISPU. This information is used by the ISPU tools during generation of the output files. Double-click on conf.txt to open it. The conf file from the template project already contains a minimal configuration for the project. We can see that the accelerometer is configured in high performance mode with an ODR of 26 Hz and full scale of AG. We can also see that the ISPU is configured with an IRQ rate of 26 Hz and interrupt 1 is enabled in pulsed mode. Lastly, we see that algorithm 0 is enabled and that interrupt 1 for algorithm 0 is also enabled. We'll leave these parameters as is for this project. Information about these configuration options can be found in Help, Help Contents, ISPU Tools Documentation, ISPU Gen. We can close the conf.txt file now. The next file we see is meta.txt. This file contains metadata which will be added to the output files. It can be used to provide information about the outputs of the ISPU, such as position, data type, and length. We'll use this file later on in the project to describe our algorithm outputs to the Algobuilder tool. Lastly, we have the shub.txt file. This file contains the sensor hub configuration to add to the output files. It can be used to configure an external sensor attached via the sensor hub interface, as well as configure the sensor hub to read data from the external sensor so that it can be processed by the ISPU. Information about this file can also be found in the Help menu. We will not use the shub.txt file in this project. Next, let's look at the folders present in the project folder. The Includes folder lists several locations from which include files will be loaded. The ISPU utils folder contains utility files, which you will normally not need to modify. CRT0.s is the low-level startup code containing our interrupt vectors. Global.s contains macro definitions for the project. Boot.ld is the linker script which defines the project's memory layout. Peripherals.h contains useful defines that will be used in our projects. Regmap.h defines the addresses for various ISPU registers used in our project. Let's take a quick look at this file's contents. Double-click on regmap.h to open it. We can see defines for various configuration, flag, and status registers. In this module, we'll be reading data from the accelerometer registers and outputting data via ISPU output registers. The output registers are called ISPU_DOUT. Note that each data out register is 1 byte in size, and they are grouped in pairs. The first two data out registers are ISPU DOUT00L and ISPU DOUT00H. There are 32 pairs of data out registers. This information will be useful later in the project. Now scroll down until you reach the accelerometer and gyroscope registers. These are called ISPU_ARAW for the accelerometer and GRAW for the gyroscope. The name then specifies the axis X, Y, or Z. Our algorithms can use these registers to read accelerometer and gyroscope data from the sensor. Next, expand the source folder. The source folder contains a single main.c file. This is the main source file for the project and is where we will add our code to implement the roll and pitch angle calculations. Double-click main.c to open it in the STM32Cube IDE editor window. As we scroll through the file, we see that the template contains two functions, algo00init and algo00. These are the initialization and worker functions for algorithm 0. The ISPU can run up to 30 algorithms. Each algorithm will be implemented in similarly named functions. For example, algorithm 1 will use functions algo01 init and algo01, and so on. As mentioned, the function algo00 init is an initialization function for algorithm 0. Initialization code for the algorithm should be added here. Note that this function only runs once, whenever the ISPU is enabled. The function algo00 is where the algorithm is implemented. The ISPU is normally in a sleep state. When new sensor data is available, the ISPU wakes up and this function is called. The function processes the new data, generates any outputs, and then terminates. Once all the algorithms have run, the ISPU enters a sleep state again. Lastly, we have the main function. This function initiates the execution of each algorithm when new sensor data arrives, and then raises an interrupt to the host MCU when all algorithms have completed their execution. You do not normally need to modify anything in the main function. Let's implement the roll and pitch angle calculations. ST provides a number of design tip documents on st.com. One of these explains how to compute tilt measurements from accelerometer data. You can find this document by searching for DT0058 on ST's website. We'll use the information from that document to implement our roll and pitch demo. A copy of the document, as well as source code for the calculations, is provided in the folder c:\studio-workshop/module8/DT0058. Let's open the source code file, which we will use to implement our roll pitch algorithm on the ISPU. Open Windows File Explorer and navigate to c:\studio-workshop/module8/DT0058. Right-click on the file dt0058example.c and select Open with Notepad. The first function we see is algo00 init, the initialization function for algorithm 0. As we can see, the function is empty, since the algorithm does not require any initialization. Now let's look at the algo00 function. Here we start by declaring some temporary variables. ACC is used for storing the 3 raw accelerometer readings for each axis, x, y, and z. The phi and theta variables are used to store the calculated roll and pitch angles in radians. Finally, the roll and pitch variables store the values converted to degrees. Let's now look at the implementation. The first thing we do is read the raw accelerometer data from the 3 input registers for the accelerometer, ISPU, a raw, x, y, and z. We use the accelerometer data to calculate the roll and pitch angles in radians using the formulae from the design tip document. We then convert the values from radians to degrees and output the values via the ISPU output registers. Note that we output the values as floating point numbers. Since the float type is 4 bytes in size on the ISPU, the roll is output via ISPU registers ISPU DOUT00L through ISPU DOUT01H, and the pitch is output via ISPU DOUT02L through ISPU DOUT03H. The last thing that happens in the algo00 function is setting the interrupt bit for algorithm 0. This indicates that an interrupt should be generated for the host MCU to indicate that algorithm 00 has completed and output data is available. To save time in this workshop, we'll copy the code from this file and paste it into our algorithm 00 function in the ISPU main.c file. First, let's include the required math.h header file. Scroll to the top of the file and copy the line pound include math.h. Return to Cube IDE and paste it in the main.c file. Just below the pound, include stdbool.h line. Next, let's copy the algorithm code. Return to Notepad and select all the code inside the algo00 function, excluding the setting of the interrupt bit since this part is already present in the ISPU template file. Then right-click on the selected code and click Copy. Return to STM32Cube IDE and paste the code inside the Algo00 function, just below the line that reads To do, read, and process sensor data. Right-click on the line and click Paste. We are done with the sample code. Return to Notepad and close it. In our Algo00 function, we need to make one small modification to the roll pitch code. We need to account for the different orientation of the ALSM6DSO16IS sensor on the IKS4A1 board with respect to the orientation used in the calculations described in the design tip document. We need to swap the accelerometer X and Y axes. We can do this by simply assigning the accelerometer Y-axis reading to ACC0 and the accelerometer X-axis reading to ACC1. Make the change in the file by replacing ISPU A raw X with ISPU A raw Y for ACC0. Then for ACC1, replace ISPU A raw Y with ISPU A raw X. Now save the file by clicking on the Save icon. Now that we have added our program code, let's return to the meta.txt file. In this file, we will need to add ISPU output information. This information is used by the Algobuilder tool to configure the output pins of the ISPU block. Open the meta.txt file by double-clicking on it in the STM32Cube IDE. The file should be empty. For this module, we have provided a meta.txt file for you. Let's open the file. Open File Explorer and navigate to see MEMS Studio Workshop /Module 8 /DT0058. Then right-click on meta.txt and select Open in Notepad. The file contains a text description of the application as well as two outputs, roll and pitch, and their data types, float. These match the outputs we used for algorithm 00 in the main.c file. The ISPU tools will use this information to add an output section to the JSON file generated when we build the ISPU project. Highlight and copy all the text in the file. Then return to STM32Cube IDE and paste the text into the meta.txt file. Save the file by pressing the Save icon. You can now close the file. Then return to Notepad and close it. We have provided the necessary metadata required by Algobuilder to configure the ISPU block. We can now build the project. Click on the Build icon. After a few seconds, you should see a message in the console window saying that the build has completed with no errors and no warnings. Let's use File Explorer to look at the output files resulting from the build process. Open File Explorer and navigate to see /MEMS Studio Workshop /Module 8 /ISPU /Eclipse /Release. The file we are interested in is ispu.json. Right-click this file and select Open with Notepad. At the top of the file is some metadata which describes the file, including its type and the creating application. Below this, we see the configuration for one or more sensors. Each line in this section defines a register address and value. This represents the sensor configuration as well as the entire program code for the ISPU. This configuration is programmed into the sensor by the host microcontroller at power up. Finally, at the bottom of the file, you'll see a section called Outputs. This section is generated using the meta.txt file we configured and is used by ST's tools, such as Algobuilder, for example, to configure the output pins of the ISPU block. Please close this file once you've had a chance to look it over. We have completed the implementation of our ISPU-based algorithm to calculate roll and pitch angles. For the next part of this module, we will use Algobuilder to design an application which will display the roll and pitch data being calculated by the ISPU. Algobuilder will use our ISPU.json file to configure the ISPU block. Let's copy the JSON file to the Algobuilder folder for this module. Right-click on the ISPU.json file and select Copy. Navigate to C:\MEMS Studio Workshop \Module 8 \Algobuilder. Then right-click on the blank space in the window and click Paste. This part of the project is complete. We can now close STM32Cube IDE. We will work on the Algobuilder part of the module next. Open MEMS Studio if it is not already open. Click on Algobuilder, then click New Design. You'll be presented with the Firmware Settings window. Let's provide a location for the firmware. Click on Browse to the right of the Firmware Location box and browse to C:\MEMS_Studio-Workshop \Module 8 \Algobuilder. Then click Select Folder. For tool chain, ensure STM32Cube IDE is selected. Last, select Nucleo F401RE plus X Nucleo IK S4A1, all SM6DS016IS for the target. Then click OK. As with previous Algobuilder projects, we start with a single sensor hub block on the main design window. Let's now add the ISPU block. In the Library menu, scroll down to Sensor Hub and expand it. Select ISPU and drag and drop it to the right of the sensor hub. Next, connect it to the sensor hub by clicking on the sensor hub output pin and dragging and dropping the connector onto the ISPU block's input. The ISPU block is just an empty block right now. It has no functionality and no outputs. We will add functionality and configure the outputs by providing the ISPU.json file to the tool. However, before we can do that, we need to save our Algobuilder design. Click on Save, then navigate to the folder C:\MEMS Studio Workshop \Module 8 \Algobuilder. Now provide a file name for the design. Let's call it ISPU_roll_pitch. Then click Save. Now that the design has been saved, we can configure the ISPU block. Select the ISPU block in the main design window. In the Properties field, click on Configuration File and then navigate to C:\MEMS_Studio-Workshop \Module 8 \Algobuilder. Select the ISPU.json file. Then click Open. This will assign the ISPU program we created earlier in this module to the ISPU block. Next, set the configuration to LSM6D-SO16IS. The ISPU block should now have two output pins. Selecting the block in the main design window will also show the output pin names and data types in the information window. The last step is to display the roll and pitch angles in the MEMS Studio window. In the Library window, scroll up and expand the display category. Drag and drop two instances of the angle level block to the right of the ISPU block. Select the top angle level block. In the Properties window, ensure the Preset Values field is set to Custom and the number of values is set to 1. In the Name and the Value 1 name fields, type Roll. Leave the unit name as is. Next, select the bottom angle level block. In the Properties window, ensure the Preset Values field is set to Custom and the number of values is set to 1. In the Name and the Value 1 name fields, type Pitch. Leave the unit name as is. Now we can connect the roll and pitch angle level blocks to the ISPU outputs. Click on the top output pin on the ISPU block. In the description window, it will show whether this pin is the roll or pitch output. Connect it to the corresponding angle level block. Repeat the process for the bottom pin. We are now ready to build the project. First, save the project by clicking on the Save button. Next, let's generate the code. Click on Generate C Code. If you get a pop-up window warning you that the directory has not been initialized, click on Overwrite. After a few seconds, you should get a message confirming code generation is complete. Let's now build the project. Click on Build. The build process may take a few minutes. Please pause this video until your build is finished. You will get a message indicating the build has completed in the console window. We can now flash the firmware to the board. If not already connected, connect the board to the PC using the USB cable. Wait a few seconds, then press the Program Target button. A new window will appear which shows the progress of the programming process. When completed, you should see a message indicating success at the bottom left of this window. You can then close this window. Now click on Connect. Ensure the communication type is set to serial and that the correct COM port has been selected for your board. Next, click Connect to connect to the board. The Algobuilder evaluation window should appear after you have successfully connected to the board. Press the play button in the top left to start streaming data from the board. You can select the roll and pitch displays to view the roll and pitch angles as you tilt the board. You can also use the Custom Layout window as we did in Module 6 to display both roll and pitch angle level widgets on the same screen. Click on Custom Layout to open the Custom Layout window. Delete any existing widgets if the window is not empty. Now select 2x2 blocks to display the roll angle level. Repeat the process for the pitch angle. Now when you tilt the board side to side and backward and forward, you can observe both pitch and roll changing. Once you are done testing your application, you can press the Stop button. Next, disconnect from the board. Click on Connect and then Disconnect. In this module, we saw how to create an ISPU project, starting from an ISPU project template. We looked at how we can add our own code to read and process sensor data and output the results. We learned how to build the project and which files to use to program the ISPU. Lastly, we used Algobuilder to quickly develop an application to read the output data from the ISPU and display it in MEMS Studio. This completes Module 8.